Okay, welcome everyone. Today we're going to see a very short introduction to computational social science. And I mean, it's related to many of the topics that we've seen already, now applied to sociology. And a bit of history. I mean, you might know that somewhere in the middle of the 20th century, there's this famous essay by C.T. Snow titled The Cultures. And basically he devised the so-called hard sciences and the humanities. And of course there are relevant differences, but kind of highlighted some of them. Since then, many institutions have followed these distinctions. For example, here in our university, we have a coordination of scientific research and a coordination of humanities, and they're separate and have different evaluation mechanisms, and we make jokes about each other. And I mean, let's speak about some of the origins of the differences. So, science aims at being reproducible and objective and predictive and many other things that achieves to different degrees of success. So, for example, in physics, at least the one we are taught in high school, let's say there are several examples of phenomena that can be isolated and reproduced and, let's say, experimentally explored. And it doesn't mean that in physics there are phenomena that are difficult to explore with this approach, but the fact that in other domains, like sociology or psychology, you cannot isolate successfully, say, a society or even a person and make isolated experiments that are reproducible. And well, there's lots of external factors or internal factors that make almost every moment unique. So it's not so trivial to generalize laws as it is the case in simpler phenomena. That, for example, since there is no difference between any atom of hydrogen, since they're all the same, so it doesn't matter whether we pick one or another atom of hydrogen, we'll have the same properties as far as we can tell. However, for individuals, animals, people, not only every person is different, but they also change in time. So, of course, this is a challenge, for example, for medical studies, because the same medicine will not react in the same way in different people. And of course, this poses challenges that, I mean, they have been overcome more or less different degrees. And another thing is that the number of interactions that we usually study in the so-called hard sciences are relatively low until recently. So, for example, the M-body problem, we mentioned at the beginning of the course that Newton described the two-body problem, the law of gravitational, the universal law of gravitation, and only until the end of the 19th century, Poincaré didn't precisely solve the three-body problem, but showed that it was what we now know as chaotic. Actually, it doesn't have it's difficult to predict because of its chaotic nature, with three bodies. And for example, in chemistry, also the universe of possible reactions is huge, even considering most reactions that are studied are with those three, maybe four elements of compounds. And then you see what happens. But in principle, you could have many more elements, but then it's much more difficult to control because everything, if you change the concentration of one of them, then that might affect others. So of course, that restricts an exhaustive exploration of of the chemical space. In biology, we still can study certain aspects of some animals in isolation, but of course not all of it, because we need to interact with our environment to survive. No living organism can survive in isolation. And if we're speaking about societies, it's senseless to study individuals in isolation. So let's say the methods that were used to study 1, 2, or 3 bodies, physics and chemistry, are simply not appropriate for studying societies. However, the methods that have been developed to study n-body problem or supramolecular chemistry, complex systems in general that we have seen, they are appropriate for studying societies and ecosystems. So we can say that what limits or what used to make soft sciences soft was precisely their inherent complexity. And it's not that other disciplines don't have complexity, it's just that if they could get away by ignoring it until recently. They could get away with it because there were examples of successful phenomena that can be successfully described in relatively isolated states, which is not the case for biology. It's somewhere on the edge, but higher levels of study like societies, ecosystems, economies, it's already not possible. Cultures. We have spoken a lot about complexity. Just as a reminder, complex system is characterized by interactions. So the more interaction you have, more complexity you have. So, for example, you cannot predict what will be the future of a person if you don't consider the interactions they will have along their life. So they might have good influences or bad influences at school, and that will determine how they develop, let's say, with, of course, their potential that they carry through genes and genetics, what they will bring forth to the world. And just like computers can serve as telescopes for complexity, the same computers have been useful to study social systems in a similar way as the rest of complex systems. And of course, this is related to computational predictability, as I mentioned, that you cannot prestate the future of systems, you cannot predict, or so your predictability is limited because the interactions that will occur cannot be foreseen until they occur. So it doesn't mean that there's something magic going on. It's just that there is a process that cannot be reduced. There's no shortcuts to the future. Another component that's problematic it's that of downward causation, which many people still believe that there is no downward causation physics. Then when I speak with biologists and sociologists, they say, well, how would you explain life and society without downward causation? I mean, it's kind of very intuitive to say that individuals make social norms or laws or rules, and then these higher level social structures, the individual behavior. So that's like a top-down influence. We see it with traffic. Individuals make traffic signs and traffic rules, and then drivers don't follow those traffic rules, or we try to follow those traffic rules. But in any way, it influences the driver behavior. So we can say that's a top-down influence. And another interesting example that I learned recently listening to Lex Friedman's podcasts. Recently, he had Sari Mary Walker and Cronin, and they were speaking about assembly theory. So they give the example of a plastic bottle, meaning that in order to describe what's a plastic bottle, you need to describe all evolution of life, because say we did that plastic bottle doesn't matter, but it's not a living system, but it has to be made by living systems. It's not something that could arise without a civilization. So taking from that example, I guess we can say that that's another example of downward causation, in the sense that plastic bottle is a physical object. It occurs at a physical and chemical level of life. So, say biology, in principle, doesn't rule over its existence. But if you don't consider biology and sociology and economics, you wouldn't be able to explain how in the universe plastic bottles came to be and with which purpose. So I think that's another example of downward causation, because we create these objects that might be inanimate, and everything around us is created by us with a specific purpose. And it's not that we are violating the laws of physics, it's just that it's biology acting on physics in a downward way. Therefore, if you just look at the laws of physics, you will not be able to predict this type of objects in the universe. So we also mentioned the example of money, that it's, let's say, not of a physical nature, but more of an informational nature, and it has a causal influence in matter and energy. So it's just one of many examples of higher scales changing lower scales. And I think that we're only developing the tools to study this because logically we don't have the proper tools for understanding downward causation. I mean, we usually start from axioms and then develop theorems, but in our formal systems, the theorems cannot change the axioms. Otherwise, I mean, it's kind of against the rules of formal systems. So I don't know whether we will manage to come up with a new kind of formal systems that can circumvent this limitation, and then there will be new possibilities. But so far, this limits what we can do with artificial systems, and probably next class we'll speak more about these limitations. So already in the end of last century, in the late 1990s, there were different works by different people speaking about artificial societies. So it's actually the artificial was very popular in last century. Of course, began with artificial intelligence, but then Herbert Simon wrote his book, The Sciences of the Artificial. I think the first edition was in '68. And he speaks in general about doing science with computers. And in a more recent edition, like the third edition from the 1990s, he already is explicit about complexity. And we already mentioned that artificial life was coined in the 1980s, a bit opposing classical AI. So artificial societies were following the same path. I mean, not criticizing artificial intelligence because it's already different, but using computational tools to model social systems. Actually, my bachelor's thesis was on artificial societies back when the term was still popular, but in the years that followed, the name kind of changed to computational social science, which, I mean, at at the end it's more or less the same thing. So it's just like with other complex systems, to use computer models, simulations as models of the real systems using this synthetic method that we've mentioned, that instead of observing a real phenomena, making experiments and making predictions, and then testing those predictions of the theory that makes those predictions with a real phenomena, you do a simulation or you build an artificial system, and then you make predictions with that system, and you observe, and then you reproduce what you observe in the real system. Then you might think that you are reproducing some essential aspects of the real system. But actually, there's an interesting philosophical paper as some of my teachers and subjects, and the title is something like Computational Simulations as Opaque Thought Experiments. And their argument is that, I mean, of course, simulations can be useful, but of course, the fact that you get similar results in a simulation doesn't mean that the real system is explained or behaves in the same way as a simulation. So, I mean, this can be seen in a very abstract way. Imagine you have a function in an n-dimensional space, so some curve. There will be an infinite number of functions in an n+1 space that go through that function on an n space precisely. But then you cannot tell which one is the real one. And we see that with many computational models. So one of the ones we've seen, the preferential attachment of Barabasi-Albert, that grows scale-free networks. It grows scale-free networks, but it doesn't mean that all scale-free networks that we observe in nature do that mechanism. So in a similar way, we can make some mistakes by assuming that our computational model reproduces observed phenomena, then the rules of our model are the same rules that the real social system is using. I mean, that they have the same mechanism. And it might be that it's just different mechanisms that exhibit the same properties. So we have to be careful with that. And of course, we can speak about universality classes and what we mentioned. The best way of understanding a system is by building it. So of course, if you can reproduce some properties of a natural system, it gives you at least some insights on what is required, what are necessary and sufficient conditions for that dynamics to observe. But that doesn't mean that you are proving something. So I mean, just be careful that there are limits to computational methods. However, there are many things we can do with these methods that have been very powerful. Of course, we should take advantage of this. So one of the things that have enabled computational social science, we already spoke about this, is the huge amount of data that has been gathered in recent years. So there has been an exponential increase of data gathered. I don't know whether this rate still maintains, but until recently, the data that our civilization had produced was doubling every 2 years. So, for example, the amount of data produced in 2021 to 2022 was similar to the same amount of data produced from the origins of writing to 2020. And this has continued. So, I mean, there are plenty of data sets available that allow us to test different theories. So, for example, well, there's some links to databases. Seshat's databank, I'll speak more about it. It's made by historians. ICON is managed by Prof from University of Colorado. And there you can find a huge repository of different networks. And the Google Ngrams we already have mentioned. It's a huge collection of linguistic data. in different languages. So it seems that with computational social sciences, these are becoming harder in the sense that we are able to contrast different theories. Before, they were called soft because since you were not able to test your theories, you should remember this idea of the analytical method that you have an observable, then you make a theory, and then that theory you make predictions, and then you observe some new experiments that will validate your theory. But in sociology, it's very difficult to replicate conditions because everything is changing already. As in history, it's like, oh, what would have happened if, I don't know, some decision was taken in history in a battle? Well, would the result be different? You can't make those experiments. So many sociological and historical, psychological theories were left at the rhetoric level. So it was an argument like, okay, which one is more convincing? And actually, a good example of that is talk by Danny Bassett. She gave at the C3 colloquia. So if you go to the C3 channel, search Danny Bassett, you will find her talk. She gave, I think it was last year or this year, I forget. And some of the work she did precisely trying to contrast different theories of how we do science. So if you take a basic course on philosophy of science, you will learn about different theories of how science is made. So there's the theory of Kuhn, of the revolutions. I think she also covered Lakatos and Feyerabend, maybe. Well, three theories. I think it was these three theories. I'm changing one theory for another. But then she saw how, let's say, with Wikipedia data of how pages change, they were able to test experimentally these different theories. And they found that actually Kuhn's model is the one that is consistent with how Wikipedia changes. So that's interesting because now you can say, okay, this theory has been validated and these two theories have been falsified. Like that, there are other examples where now we are able to contrast different social theories, and this is making social sciences harder. Of course, there's also a book by Sandy Pentland, also the title is Social Physics, and it's also going in this direction. If you want to know more about this, you can check out his book, Social Physics. And what allows this is many methods and models which are, they're not trivial to be adopted by the traditional sociology community, but they're doing it. But first of all, in sociology, people are not taught how to program, but many sociologists are learning how to program by themselves. And fortunately, this has become easier. In the 1980s, it was much harder to program than it is nowadays. There are tutorials everywhere, languages are simpler. So many students are also digital natives are learning to program. There's lots of data. We also mentioned the agent-based models. So this allows the computational modeling of systems without having an advanced training in mathematics. Network science is also quite accessible. And also interdisciplinary teams are making many advances because, of course, in some cases, you do need to make some more thorough analysis, but then, of course, this can be made only by physicists because they don't know backgrounds with the sociology. So many interdisciplinary teams have made significant contributions in this area. So let me just share some of the work that we've done in this direction. So it was part of the PhD thesis of Luis Enrique Cortés Berrueco, already some years ago. So we took basically traffic models, highway models, and game theory. So with game theory, most classical lemma is the prisoner's dilemma. So we have operators and defectors. And what we did was to simulate cooperative drivers and selfish drivers with defecting drivers. So basically, a cooperative driver will not cut to other cars, so they will change lane only if there is enough space so that other vehicles don't have to brake. And the selfish drivers will change lanes if it's good for them, even if that causes a delay in other vehicles. So as we can see here, for low densities, actually the defectors or the selfish drivers drive faster, and also for higher densities, but for medium densities and for very high densities, it's the same. So basically, there's not much space to change lane. So one might say, oh, and it's more efficient to have selfish drivers. But then if we look at the probability of accidents, so the rates of emergency brakes caused by lane changes. So how often when a vehicle changes lane, another vehicle has to make an emergency brake because otherwise they would crash. And well, the y-axis is an exponential scale. You can see that in the blue line that there's less cooperation. This is much higher. So if we, well, it's another example of sometimes as engineers we focus on optimizing performance, but say if we optimize performance based on this graph, then we would assume it's more effective if cars were selfish, so design selfish autonomous vehicles. But it turns out that this increases risks. So if you don't consider this, you might make the wrong assumptions and end up with lots of accidents. Of course, the accidents are not only dangerous, but if you have an accident, then you will block a lane for a long time, and that, of course, decreases the performance. And this other work, which is still for my PhD thesis about organizing bureaucracies. So the idea is an abstract network of agents that can be individuals or departments or ministries. They have dependencies with each other. So, for example, one department might request another department some task, and then that department can request other departments for more tasks, like that. And you create networks with different topologies. And then there's a very simple adaptation that you change the dependency of the agent with the longest queue towards an agent with the highest delay to the agent with the shortest queue, and with very few. Yes, so here, for example, you can see how I think these are the tasks that are being completed, and these are the length of the queues. You can see here that there are very few agents that have very long queues. This has the longest, and these two, but most of the agents are idle. So if you do some basic rewiring with very simple rules, you can reduce very quickly the bottlenecks and have performance that is similar to the theoretical performance. So in principle, we could apply these ideas to our bureaucracies and improve services, but some might say that the purpose of bureaucracies is not to be efficient. So that will go against the purpose of bureaucracy. So it's like an oxymoron on efficient bureaucracy. So many of the things that we are learning from computational social science and computation in general is focused more on interactions rather than on its components. Of course, components are relevant, but if you don't notice interactions, then you won't be able to reach many consequences. So, I mean, this applies also for complex systems in general, not only for social systems. Of course, we have several challenges to, say, really reinforce the potential of computational social sciences, but in my case, these are more human than technical or scientific. We mentioned already this. So, for example, there's this potential of improving bureaucracies, then how to find the bureaucracy that would be willing to implement this improvement. That's much more difficult. Where we can find solutions to improve how people drive, then convince politicians to implement those changes. That's much more challenging. And another challenge is also how to develop a common language, not only between the so-called exact sciences and the social sciences, but also between the different sectors, academia, government, society, the private sector, and so on. Okay, so just before going to questions, a few date announcements. So Thursday, the next two Thursdays, so this week, next week, Thursday, the class will be only online because different motives. This week, it's semi-holiday, the 5th of May, here, and then next week there will be some event at the auditorium, so we'll just meet online. But next Tuesday is a holiday, so we won't meet. So yeah, next two classes will meet online, which will be 2 days from now, next week Thursday, and then on the 15th, on the 17th, we'll be back here at the auditorium. And that will be the last week's, the last class is May 25th, and the final project should be delivered before June 9th. I already made an entry in the Google Classroom so you can upload your final projects there. So ideally, the last week, meaning May 24th and 25th, there would be like the final presentations of your final results. So it would be good that you have already the results, and then you still have a couple of weeks to write the report about those results and include any feedback that might arise. So, yeah. Are there any questions or comments? Oh, see the chat. So, Odina, jokes. Peter Turchin, the Harry Sheldon of real life. Sheldon is from the what's the name of the series? I think I know who you mean, but I think not. Yeah. Okay. Different Sheldon. Since I haven't read Asimov, I won't be able to tell.
Harry Sheldon is the character in the Foundation that develop a mathematical technique to understand the process of history in the future, or something like that. So Peter Turchin is actually pretty similar.
Yes, I remember it's psycho something or
psychohistory.
The name of this. Yes. Yeah, the name that Peter, well, he's originally Russian, but has lived in the States already for decades. The name he used originally was Cleodynamics, so Cleo, muse of history or goddess of history in English. I forget whether muse or goddess, but she's associated with history. Cleo, and dynamics. Well, yeah. So he kind of tried to find historical patterns already for quite a while, and he was revolutionary in a way because he was using mathematical models in history, and that was unheard of in the 1990s. And actually, I know because of him, because of his father, Valentin Turchin. He has a very interesting book called The Phenomenon of Science. So Valentin Turchin, he was collaborator with one of my PhD advisors, Francis Heligan and Steve Jocelyn, on a project which was called Principia Cybernetica, which last century was like one of the first resources for cybernetics, AI, and things like that. So it was kind of an early Wikipedia of cybernetics, but yeah, I mean, it was like edited and with authors for different pages and crosslinks. So it was interesting and useful resource back in the day. And Valentin Turchin was repressed by the Soviet regime because he had ideas that were not aligned with, I don't know whether to call it Marxist philosophy. So he migrated to the States at some point. I don't remember whether in the late 70s or early 80s. I think he was in Columbia University. Maybe I'm mistaken. And then, I mean, I've met Peter in conferences, and we've exchanged emails and so on. But I mean, I don't know his story of how he ended up studying history in University of Connecticut. But from his father was, let's say a hardcore cybernetician. He surely got the formation of doing history in a non-standard way. So yeah, that's an interesting thing. And also, Peter Chen has been the coordinator of this Complejidad data bank that I mentioned. Complejidad is the goddess, the Egyptian goddess of history. That is a goddess, not a muse. I don't know about Cleo. And I think I mentioned this at some point that so he kind of organized a whole community of historians to upload in these databases structured data about different civilizations from different regions of the world, different times, and then using different statistical methods over these structured data, they were able to contrast different theories. So yeah, I think I already mentioned that there was this theory that in order to have large civilizations, like 500,000 people or more, you needed moralizing gods. Yeah, well, religions with moralizing gods or moralizing religions, meaning that in order to solve conflicts between individuals, between groups of individuals, you need to have like a religion that tell, okay, you shall not kill, you shall not steal, you shall not whatever. That we observe in many religions. Then they had this data and they put this theory to the test and it failed. And actually it turned out to be the opposite, that first you grow civilizations of history, but that's what has happened repeatedly in our planet, that civilizations first grow to a certain scale and then they develop these moralizing religions. And they try to explain why this is the case. But I mean, it's an interesting example of how, I mean, we could say history is becoming harder. And in this case, it's not because they kind of reproduce in a simulation different possible trajectories of history and they abstracted something from it, but by gathering lots of data and then doing statistical analysis on this data, they were able to, I mean, not necessarily reproduce, but to be able to have data with enough statistical significance to verify or falsify different theories. So yeah, I don't know whether to call that experimenting, but basically you gather enough data to be able to contrast theories. And if you have just one data point, then you can do statistics on that. Which some people say that that's the problem with biology, that we just have one biology, the one on our planet. So we need more examples of extraterrestrial life in order to be able to understand better our life, life in our planet. Because it's difficult to make generalizations or predictions with just one data point. But yeah, it also depends at which scale you observe it. Because if you don't consider, say, life as we know it as a single thing, but if you look at different species or different individuals, then of course we have more data than we can handle. Yeah. More comments? Or are there some examples that you know that might resonate with computational social science? Either something that you know about that's really interesting, or something that would benefit from computational social science? Like, why isn't this totally? Which faculty is sociology? Philosophy and letras? Yeah. Yeah. Right.
Hi. I have doubts yet with the downward causation, and specifically with the example you gave about the plastic bottle. So downward causation means that simple systems with less complexity than others are dependent. Changes in systems with less complexity are attained by the higher system. So with this example of the bottle, the higher system are the humans that made the bottle, and the downward causation is that we manipulate the molecules and the materials to create the bottle.
Yeah, I mean, the downward causation is not so much about higher complexity, but higher scales of organization. So, I mean, we can describe the organization of matter like atoms, molecules, cells, individuals, and so on.
Yes.
So, traditionally, reductionist science assumes that causality just goes one way. Meaning that elementary particles determine atoms, determine molecules, and so on. So, for example, even the game of life doesn't have downward causation because you have the simple rules, and you have emergent properties, but the gliders, and spaceships, and everything that you see, these don't change the rules of the cells. So you need to study the interactions, but there's no downward causation. And also, in the philosophy of science literature, most of the works that deal with downward causation have to do with consciousness, which is very problematic, more because of consciousness than because of downward causation. So that's also why many people kind of try to avoid this topic because it's controversial. And there are people who say that no, there is no downward causation, and say there is, and there is weak downward causation and strong downward causation. And it's basically the difference of perspectives is that if there's no downward causation, then you assume that if you have a full description at the lower scale, then you can derive everything that happens at a higher scale. And my argument is that you can't, you cannot describe what will happen at a higher scale because of computational irreducibility, but you cannot describe what will happen at the same scale because of downward causation. That the structures and organizations that arise in the individual interactions at the lower scale, they will generate constraints and will change the rules of the lower scale. And the fact that our formal systems cannot handle this doesn't mean that it doesn't exist. And these examples are like that. It is there. This chair is there. It's as real as whatever you want.
Yes.
Follows the laws of physics, but physics are not enough to explain what it's doing there and why it has this shape. Because of course you need to consider the anatomy of humans of a certain size that will use that chair.
Yes, of course. And upward exists?
Yeah, that's what most people, when they speak about causation, it's either upward or on the same scale.
Yes.
So many emergent phenomena are upward causation.
Yes.
Like flock of starlings, interaction between individuals, and then you have the patterns at the flock level.
Of course. Yes.
Or lives. But individual molecules are not alive, and they interact, then they produce something we call life, whatever that is.
Okay. Thank you.
Yep. Any other comments? Okay, so there was a quick touch. So we'll meet on Thursday online. And probably we'll speak about the limits of artificial intelligence, but it's also a bit extending some of what we spoke today. And it's some ideas that I've been thinking about just recently. So it will be something in the process of being developed, but I guess it will be useful to bounce the ideas against you. Okay. Thank you.
Thank you.